Hi, everyone. This is a joint work with my students Zijian Huang and Wang Qianli from the Penn State University. And Zijian Huang was the Master of Science student and now is a PhD student. And we complete this work through remote supervision during the COVID years. So it's kind of very significant for us. Okay, so I don't think I will go through all of them. So maybe I will leave maybe a few minutes in case that you might have questions to ask. Okay. So the representation learning is all about the expressive power of the representations that we can learn from the data that we're dealing with. So if we are dealing with the knowledge graph, it is the entity and the relations that we want to learn. And we want to capture the relational behaviors from entities to entities in this knowledge graph. And also, we also want to preserve the closure properties that under the relational logical operations. And the logical operation, we do mean the intersection operator, union operator, and the negations of operators in the representation space. And so we all learn these logical operators in our discrete mathematics in stage 2 class. But what we are trying to do is perform all these operations and the relational projections in the representation space. So in particular, we wanted to support both hierarchical and non-hierarchical relations. So over here, we demonstrate what is the hierarchical relation. For example, we know that North America contains USA. We also know that USA contains the city of Chicago. So the containing relationship is actually hierarchical. So we can say that North America contains the city of Chicago. But if we wouldn't be able to effectively capture this hierarchical relationship, then, for example, in a very well-known representation space, which is called beta representation space, it wouldn't be able to capture this hierarchical relationship between the entities in the representation space. That's why we wanted to propose a new representation, which is called line representation, so that we will be able to not only capture the hierarchical relation, but also the non-hierarchical relations. Okay, so hierarchical relations, here we have more examples. Okay, so for example, we know United Kingdom contains England, and then England contains the city of London. So the green relation is actually hierarchical relation. And we know that it's anti-symmetric because UK contains England doesn't mean that England contains UK. So it's anti-symmetric. And it's also transitive relations. So we know that UK, through these content relations, it contains London. But there are other non-hierarchical relations, for example, adjourn. We know that England adjourned with Scotland and Wales. So this is the semantic relations. And lives in is an anti-symmetric relation, but it's not transitive relations. And so we have this type of knowledge graph that consists of quite a lot of hierarchical relations. And so we want to come up with the effective representation learning approach such that we'll be able to capture the hierarchical and non-hierarchical relationship, but also at the same time, we want to perform the first order logic query in the representation space. So let's try to look over some of the terminologies. So what is the first order logic queries? Over here we have an example. So we know that 2008 Beijing Summer Olympics. It was held in Beijing, China. And then what is the participant countries in this Summer Olympic? So actually V1 is actually a set of countries that participate in these Olympic events. And then for this type of query, in terms of the knowledge graph terminology, what we did is just performing a relational projection. So we need to be able to given this Summer Olympic entity, and from there we want to perform a relational projection such that we will land it at the exactly correct set of countries in the representation space. And since this only require one relational projection, so we refer it as the atomic relational query. But there are more complicated queries. For example, we might have this. Well, first of all, we need to perform a relational projection, and in particular, is a participant relation. And then so from here, this blue entity, we perform a relational projection. So we got V1 is referring to a set of countries. 1952 Helsinki Summer Olympics, it performed another relational specific projection, and then we obtain another set of entities, V2. And from V2, we want to perform a negation operation so that we will come up with the complement of the set of V2. And from here, we want to perform the intersection with the set of country that is represented by V1 variable. And then after the projection, it's still a set of countries, V3. And from there, we want to perform another relational projection, contents, which is a hierarchical relation. I want to obtain the final target country, CT. So the answer for this query is actually Suva. Suva is a capital city in Fiji Island. So V3 is Fiji, which is a country, and V question mark, this is our target answer. This is the Suva. So we have the atomic relational query and also the compositional relational query. So we already know that what is the complexity consists in this type of problem setting. We need to be able to perform logical operations, intersections, negations, and also union. And then we also need to be able to perform relation-specific relational projection. And given a knowledge graph, we might consist of like more than 200 different relations that the interaction between different types of entities. So we wanted to be able to quantitatively to estimate the hierarchicalness of each type of relations. So this example, we are looking to the WordNet knowledge graph. And then in total, it consists of 11 relations. And not each of the relation is hierarchical. So for example, similar to, if A is similar to B, that means that B is similar to A. So this is not hierarchical relation. But for example, hypernym is a hierarchical relation. So we come up with two, which are already quite well established in the literature, trying to estimate the hierarchical degree of the relation, which is Kronkenhardt score and also the curvature score. So based on this, we know that part of the relation actually is quite hierarchical. And then we do have some other relations that is not hierarchical. So then from this, based on this observation, that our goal is that we wanted to be able to learn the projection representation, projecting behavior, and also the logical operators, so that we'll be able to accurately capture the anti-symmetry and transitivity relation, type of relation in our knowledge graph. Okay. So this is our formal problem formulations. We've been given a multi-relational knowledge graph G that consists of a set of entity V, and then also multiple relations R. And then we are also given a first-order logic query, Q, such that we wanted to be able to perform relational and logical operations that consist in this query, so that eventually we will be able to answer this query, Q. So we want to develop this logical query reasoning mechanism so that we'll be able to support those logical operators and also support the very complex set of relational projections. And in particular, the set of logical operators we want to support is the intersection, union, negation, and also various type of relational projection. So different research work, they might target different set of operators, then they might need another different reasoning mechanism to support a different set of logical operators. So this is the overview of our architecture. So basically, it consists of three components. Well, first of all, given this logical query, okay, it can be a very complex logical query, and then we have the knowledge graph that we want to ground our search process onto. And then in the first component over here, we wanted to derive the computation graph for this logical query, and then we also wanted to initialize all the embeddings for each entities in our knowledge graph. So this is just the initialization stage. So over here, we choose to use a very well-established probabilistic representation space approach, beta E, to initialize the embeddings for our for the following process. So the second component is the space transformation. Because the beta E representation, it wouldn't be able to capture the hierarchical relations. So in our second component, we're trying to transform the logical space from probabilistic representation space to a line space. So after the transformation, we landed in this pink area, which is our line representation space. So from there, we still have this computation graph, and then we have our query embedding and also the entity embeddings in line representation space. And from there, we wanted to train our relation-specific projectors. So if we have 250 different type of relations in our large graph, then we require 250 different relational projection functions. And then we also want to be able to capture intersections among multiple set of entities, and also the union among multiple set of entities, and also the negation, which is basically derived complement of a given entity set. So at the end, after that, each query that was being given as part of the input eventually will be represented as just a single dot in the high dimensional space. And then what we're trying to achieve is hoping that after we perform several operations in the representation space, our query will be very close by to the true answers, for example, SUVA, in this example. Okay. And I think I probably already run out of time. All right. Right. So roughly 3 components. So the first component, we wanted to derive the entity embeddings and also derive the computation graph. So what we have been given as the input is the logical query itself, logical query, which is the yellow one, and also the large graph. And then our output is the computation graph and all the embeddings for the entities. And over here, because this is the initialization stage, you can choose any existing embedding approach to embed your large graph. Okay. In the second component is the logic space transformation. So we are given the entity embeddings in beta distribution space. And our goal is to come up with the entity embeddings in line representation space. So it is just the transformation between 2 different representation space. Okay. In our third component, we wanted to be able to capture the projection and also the logical operation behavior. So we design our representation, which is the line embeddings. Compared to the existing probabilistic distributions representations, which is beta E. Beta E in each dimension, let's say in this example, we have in total 200 dimensions. In each dimension, beta E is a distribution. And in particular, it's a beta distribution that's controlled by 2 parameters, alpha and beta. So in total, we need to tune or learn 200 set of alpha and beta so that we'll be able to capture just single entity. Over here, we transform into the line representation space. So line representation space, you can consider it as like a histogram. In each dimension, we sample a few data points, k. So in this example, we have sampled 3 data points in 1 dimension, and in total, we have 200 dimensions. So in total, we use 600 data points, trying to capture the representation for a single entity. And then we choose to use the histogram rather than a presumed distribution. It's because we want to be able to relax the distributional assumption so that we can capture more different complex behavior of the entities in representation space. So after we perform the space transformation, so we transform from beta E type of distribution into these line representations in high dimensional space. And then after that, it will be the logical operations that we need to capture. So in particular, we have the relation-specific projection. So if we want to perform contents, a projection for contents type of relation, we need to learn the neural functions to perform this transformation. Or the adjourn is another relation. We require another set of parameters or another neural functions to be able to perform that specific projection behavior. And then we have the intersection operator. So basically, let's say if I have two entity set, the first entity set is the red distribution, and another entity set is the blue distribution. So the intersection of these two distributions, it will be something in the middle. So in the beta representation space, it will be something like this. But in line representation space, it will be something like this. So it's still a histogram type of distribution, but it still wanted to capture the intersection behavior of these two histogram distribution. And then we wanted to make sure that this is generic enough so that it can perform for n different entity set. So not just binary intersection, but many intersection for many different entity set. And then we also have the union operator. If we have two distributions after the union, so basically we want to roughly capture the union distributions. And the negation, so let's say if we have the beta distribution is the red curve, and then the complement of that red curve is something like this. Okay. So after all this, then we wanted to design our loss function so that we'll be able to specifically capture hierarchical relations and also the non-hierarchical relations, and also all sorts of logical to regularize the logical operators. So eventually, for each given query Q, because we know what is the true candidate set, so we wanted to gauge the difference between them. And our goal is hoping that the difference between them can be minimized. So this is for the set of true, for each query and answer pairs. Then we have this MSE quantifier. And then we also sample k different negative samples so that if I'm given a query and a k set of false candidates, false answers, then we want to make sure that the distance between each query and the false answer in the representation space is greater than a margin gamma over here. Okay. So this is our overall loss function that consists of relational regularization and also the logical regularization and also the QA question answering accuracy. And because I don't have time to go through all the evaluations, but basically we just want to highlight in this type of research, what are the research questions that we're concerned of. And then this is probably something that we wanted to come up with before we conduct the research. So for example, we are concerned of whether our model will be able to accurately support the complex logical queries. And then we also want to know that whether our model will be able to support hierarchical relations and how accurate is that. And then we also want to know that how effective is our logic space transformation, because otherwise I can just use any existing KGE approach and then assuming that it might be performed very well instead of making all the effort and trying to perform this logic space transformation. And also because this model involves a lot of parameters, so which is basically the neural functions. What is the effectiveness of these relational neural functions and all these logical operations? So that's all for this talk. And then this is our team. So this is my students' work. Okay. Any questions?
Company wanted to take advantage of this approach,
yeah,
and they, let's say they have basic knowledge graphs, how difficult would that be for them?
I think it would be quite easy, as in like our model doesn't really take a lot of computational resources, and then it's already open source, so everyone can download this model, and then it also can be easily customized different applications. For example, if I'm working with medical knowledge graphs, or if I'm working with the recommendation knowledge graph between the items, purchased items, and all the users, then it can easily extend it to different kind of scenario depending on what is your application is. Yeah. Yes.
So, in the work you restricted the sorts of logical operators you were working with, but then in your example you still had the extension qualifier. Are you just like enumerating, like when you're asking, like, does there exist A, are you just enumerating all of the possibilities?
Yes.
Okay.
Yeah. So if our true answer consists of 100 different entities, that is supposed to be 100 entities, or should be in our, yeah. Any other questions? Yes.
So I understand the large language model poses a lot of challenges to a lot of traditional machine translation as well as language graph. So what do you think of this challenge? So shall we turn our focus to only on large language model, universal large language model, or we still need to focus on large language model?
Okay, so your question is that whether we should focus on the LLM or different specific type of NLP task.
Large language model can do a lot more.
Yeah. So, well, normally this is the two-stage learning process as of 2023. So basically there are two stages. The pre-training stage, we can train our model to be able to basically see a lot of corpus. And then usually in our fine-tuning stage, we will, based on what specific application that we are dealing with, we might need to fine-tune our model so that they can recognize some of the specific data that we're dealing with. For example, maybe I need to perform a drug recommendation for my model. So I cannot just import any large language model that is trained on a lot of corpus. Yeah, so they need to be able to recognize some of the data in my specific domain. But in this type of framework, we usually want to make sure that we'll be able to generalize our language model such that it can support a variety of NLP tasks, for example, sentiment analysis, fact verifications, and even the recommendation, so on and so forth. But if you really want to make sure you can use some of these techniques to address the applications in your domain, you still need to fine-tune the model. Yes. Yes.
So a related question there. So obviously you have used negation there as well.
Yeah.
So is the assumption built in that you are doing the reasoning or close words kind of
Yeah.
knowledge graph? So how will this approach translate to an open world?
Yeah, so open world means that it's possible that
You don't know what you don't know.
yeah, we don't know. And then, so this knowledge graph, maybe, for example, WordNet. So we can only, based on the knowledge that captured in this WordNet knowledge base, then we can answer some of the questions. But let's say if it's open world assumptions, a lot of things that happen on Wiki or a lot of things that happen in this world, we wouldn't be able to answer this type of questions. So open domain is actually quite challenging. And then usually in an open domain type of reasoning task usually require the techniques that is the combination of the natural language processing and also the knowledge graphs, because we need to be able to understand the natural language expressions apart from this structural knowledge. Yeah. So now there's a lot of trending research topic that was focusing on the combination of these two or even more type of modality.